How much mass could Earth lose and still remain in orbit? Can Dyson spheres be stable? And what would it take to fix the atmosphere of Venus? All this and more in this week's question show. Welcome to the question show. Your questions, my answers. Now, as always, wherever you are across my channel, if a question pops in your brain, just write it down somewhere in the YouTube comments. I'll gather them up and I will answer them here. Don't send me an email, put them into the YouTube comments. Now, we do the show live every Monday at 5 p.m. Pacific time. So if you want to come and join the live show, it's a much longer, probably triple the length, triple the length. And also we do a lot of follow-on questions. After I finish recording the show, I stick around, we do overtime. It's a lot of fun. So definitely come join the show, 5 p.m. Pacific time on Mondays. And there should be a live event somewhere on my channel that you can click and get notified. And again, I promise YouTube will remind you at exactly the right time and you'll know to come and show up for the live show. All right, let's get into the questions. David Berthlet, how much mass can the Earth afford to lose before the Earth loses its orbit? I'm going to rephrase your question in a way that I think will cause you to know the answer. What falls faster, a feather or a cannonball in a vacuum? Like obviously, yeah, you drop a cannonball on a feather, then the cannonball falls first and the feather floats down. But if you do this on the moon, the feather and the cannonball fall at exactly the same rate. So even though they have different amounts of mass, the cannonball versus the feather, we know that they fall at the same rate. And this is a test that was done from the Leaning Tower of Pisa. What is it? Galileo did it, I think. To prove that gravity is pulling with a constant force regardless of the mass. So the orbit of the Earth is due to the gravity of the sun. It has nothing to do with the mass of the Earth. If you stripped away every single piece of the mass of the Earth would continue to orbit in precisely the same rate that it does going around the sun. Now, that's not exactly true because, in fact, the sun and the Earth actually orbit around a common center of gravity between the two of them. Same thing with the Earth and the moon. So the Earth and the moon are actually orbiting around a common center of mass between them. It's located inside the Earth, but it makes a wobble back and forth, kind of like the Earth is spinning around like a hammer around and around and sort of being pulled around as it does it. But if you had a satellite that is the size of a CubeSat, it would orbit around the sun at the same rate as with the Earth. And so a lot of people wonder about this, right? They're worried that as we mine the Earth or as we send spacecraft off of planet Earth, it's going to reduce our mass and that's going to cause us to spiral in to the sun. But the reality is the laws of physics don't work that way. And gravity wouldn't make any sense if that worked. And if you had less mass, you fell slower or faster. It wouldn't work that way. So nope, no problem with Earth losing as much mass as it wants. It will still stay in orbit around the sun. You've probably noticed the codes that are appearing over one of my shoulders. No, it's this shoulder. That is a way for you to vote for the questions that you thought were the best in this episode. And so last week, the winning vote was the question about storing your sensitive electronics in a ferret cage. And obviously this was like autocorrect. Rob had wanted to say put it in a Faraday cage, but I just loved the absurdity of it being a ferret cage and answered it as such. And I guess you all thought that was funny too. So at the end of the episode, once you've seen all the questions and you've found your favorite, put in your vote for the question that you like the best. And the next week we will celebrate the winner. And thank you everybody for participating in this silly way of entertainment on the channel. Surf Sensei 60. A question I didn't hear about the concept of the Dyson sphere is whether it could be stable due to gravitational interactions, orbiting planets, etc. What do you think? So a Dyson sphere, as many people imagine it, is this rigid sphere that is orbiting around a star, is inherently unstable. And I'm sure people are like, how can you even make a sphere? That's not possible. But the reality is that if you tore apart every single planet in the entire solar system, including Jupiter, all of the asteroid belts, all of the Kuiper belts, as much of the Oort cloud as you can get your hands on, you could actually make a rigid shell around the sun that was a few tens of centimeters thick, maybe like this thick. So, which is kind of mind-boggling. So I mean, if we could somehow turn all of the matter in the solar system into some kind of unobtainium, some very dense, rigid material, then we could create this giant sphere. But it would be a very bad place to live. Like, the first thing is that, yeah, you could rotate this giant sphere around the sun so that you would have artificial gravity around the equator. But as you went further and further up or down, then you would lose that artificial gravity, and like down at the poles, there would be no gravity whatsoever. But the bigger problem is that it is unstable. When you have something in orbit around the sun or orbit around the Earth, it is sort of can maintain this orbit forever due to its velocity matching the pull of gravity. But with a rigid sphere, it actually kind of no longer is orbiting. It's now free floating and will drift back and forth with the sun in the middle of it. And you may start out, like if you just like snapped your fingers and created a sphere around a star, then the star would be moving a little bit and the sphere would be moving a little bit around it. And eventually these kind of oscillations would build up over time, and then the Dyson sphere would crash into the sun, and that would be a problem. So all ideas for a Dyson sphere are really a Dyson swarm, where you have just trains of satellites. Think about Starlink, right? Where you've got all of these satellites in a row in this long train around the Earth, but imagine that, but around the sun. It's Starlink for the sun. And all you're trying to do is capture every drop of radiation that is coming from the sun, and you're using it for some productive purpose, to run your computers, to heat your homes, to run your space air conditioners, to play your video games. Who knows what you're using it for? But that is what the sort of modern concept of a Dyson sphere is, that it's a swarm of satellites. And each one, maybe they're rotating space stations. Maybe they're just giant solar collectors that are then beaming that power to some other place. Who knows what they're doing with it? But the point being that they are individual satellites. And so, yeah, they will have gravitational interactions with the rest of the planets of the solar system. But here's the catch. You've torn up all the planets in the solar system to build your Dyson sphere. So there are no more gravitational interactions with any planets because they're all gone, turned into Dyson spheres. Problem solved. Now you can imagine there could be gravitational interactions with other stars as they pass really close, rogue planets that pass close to the solar system. But unless they really pass right down into the inner solar system with just a few, I guess, hundreds of astronomical units, thousands of astronomical units, if it's a star, you really won't see any kind of gravitational instability that's going to happen to your Dyson sphere. So really, your Dyson sphere is going to remain in place until the sun becomes a red giant. Now, you may want to move the sphere back and forth depending on the amount of radiation that's coming out of the sun. Like, as the sun gets older, it gets a little hotter. And so you may want to, say, pull back the sphere a little bit, but you may just want to keep it in place and just absorb all of that heat and photons coming from it. Sin 6 Grim Reaper 483. Has anyone calculated how much time it would take for a change to Venus's atmosphere if a fleet of satellites was placed at Venus's L1 to block some light from the sun? Yes. And I tried to find that number before the show, and I couldn't find it. And I looked at a couple of papers about terraforming Venus, and I recall it being in the several hundred-year range. And so the idea that Sin 6 Grim Reaper is talking about here is that, say you want to make Venus more livable, you want to terraform Venus. And the most direct route that you can approach this is, first, get rid of the source of energy that is keeping Venus so hot. And so what you do is you set up a giant shade at the Sun, Venus, L1 Lagrange point. This is a Lagrange question, right on. And so what that does is that blocks all the light from coming from the sun to hit Venus. Venus is now dark, and Venus will now just start to cool down. And over several hundred years, maybe a few thousand years, Venus will get so cold that the carbon dioxide that's filling its atmosphere will snow out. And instead of having this really thick, super hot atmosphere, you will have this thick layer of carbon dioxide, snow, dry ice, covering the entire planet. Now, if you moved the shade away from Venus, then everything would heat up, the dry ice would sublimate and turn into this thick carbon dioxide atmosphere. So you got to do something with it. And what that thing is you've got to bind up all of that carbon dioxide into some kind of mineral. And there's a few choices. There's like magnesium, calcium. When you think about limestone here on Earth, like there's various chemicals that you can create using carbon dioxide, which will sequester the carbon. And so someone has done the math for this, actually David Grinspoon, Dr. Funky Spoon, and he estimated that you would need 8 times 10 to the 20th kilograms of some chemical that you can use to lock it up, like magnesium or calcium. That's about 4 times the mass of asteroid Vesta. So if you could, and asteroid Vesta is not made of solid magnesium or calcium, so you need to find that, refine it out of the asteroid belt. And Vesta is like the second biggest asteroid in the asteroid belt, so you need to get it from somewhere, and then you need to take it down and use factories to mash the carbon dioxide into the magnesium to bind it into rocks, building materials, mountains. Like, it's going to be a lot. Once you've done that, then yeah, you have removed the potential of the greenhouse effect on Venus. You can remove the sunshade again, and now you can start to warm up the planet again, and it won't be locking in that heat as much. But it'll still be dry as a bone. So while you've got it sort of on the operating table, you might as well bring in many, many, many comets to bring in water to the planet again and try to make it habitable-ish. But what's kind of amazing, like there is more nitrogen in the atmosphere of Venus than there is on Earth. So there is all of the raw material in that atmosphere already. You just need to fine tune it at an industrial scale, like at a scale, the kind of scale, like as you are considering whether or not you want to build your Dyson swarm or you want to try to restore Venus. Like these are projects that will be hundreds, if not thousands away from us as human beings. The last problem is that once you start to let Venus warm up again, it's going to be continue to be bathed by radiation from the sun, the solar wind, and it has no protective magnetosphere. And people are like, why don't they just, and then come up with elaborate ways to restart the magnetosphere or the internal dynamo of a planet like Venus. Now, maybe if you cool the planet down, that's enough to restart its plate tectonics, but probably not. So it'll never have plate tectonics. It'll have an atmosphere, but it will also still have the sun trying to scour away all of the water and other elements that you've put onto the planet. And so you're going to have to either replenish them on a regular basis or build some kind of artificial magnetosphere, which I can't even imagine how you would do that. I've heard some ideas that you could build like a satellite network that is around the planet that acts sort of like an artificial magnetosphere, sort of performs the same function, where they are trying to redirect the flow of particles coming from the sun. Like when you're in space, you've got 2 kinds of particles that are coming at you. You've got the ones coming from the sun, from solar storms and things like that, and you've got galactic cosmic radiation. And the galactic cosmic radiation is the one that's more damaging to your DNA. It's the one that's going to give you the highest chance of cancer, but it's way harder to block. It's easier to block the solar wind coming from the sun. So, I mean, the bottom line is that all of this is science fiction and fantasy, but when you take the growth of humanity, you take our gross domestic product and just continue that exponential curve year after year, within a few thousand years, it's kind of inevitable, which is such a weird thing to think about. Like if you just project humanity's energy use forward into the future, within a few thousand years, we will have built a Dyson swarm. We don't know how, but the math says we will have done it. And people are like, what do we use all that energy for? Who knows? Computers. I don't know. Danny Van Wammel. How many atoms are there in the universe? According to an article on Universe Today, the answer is there are between 10 to the power of 78 and 10 to the power of 82 atoms in the known observable universe. So that is between 10 quadrillion vigintillion and 100,000 quadrillion vigintillion atoms. But that's just the observable universe. The reality is that there's must be more universe outside of the observable universe that we can see. Astronomers don't know if the universe is finite or it's infinite. It's certainly big, and it would have to be about 100 times to like 1,000 times more volume at the very least. Like if it was less than that, then we could actually detect the curvature of the universe and get a sense of how big it truly is. So it is bigger than that. So then you can just slap on another 3 or 4 orders of magnitude onto the number of atoms in the universe. Bottom line is there's a lot. Alexandros Semortsidis. Why don't we use all our telescopes on Earth and on space for the biggest resolution image ever? So there's a bunch of reasons why this isn't a very practical idea. But let's go in theory. So theoretically, if you had all of the telescopes on planet Earth and you took all those telescopes and you sent them out into space, and this is the key, where there was no atmosphere in the way, and they used all the telescopes in space and you had them all stare at one target, I don't know, some object that is not overwhelmingly bright like a star that we could see, then you would get the equivalent of the combined surface area of all of those telescopes. So you might have like the Hubble Space Telescope and the Keck telescopes and the very large telescopes, and those would be adding tens of meters of surface area, but you'd also adding up the thousands, millions of consumer telescopes, and they would all add together, and you'd have the equivalent of a telescope that added all of those surface areas together. And that sounds pretty great. Like that would be a very large telescope, and astronomers would love to take images with that big of a telescope. But practically, you can't easily do this. So there's a couple of reasons. The biggest one is the Earth's atmosphere. The Earth's atmosphere is really tough on telescopes. When you're trying to observe some object, say Pluto, from planet Earth, you're limited by how much the atmosphere is going to obscure your image. Now, obviously, if I take a 6-inch telescope, I might be able to just barely see a dot, or maybe an 8-inch telescope, maybe make out a dot of Pluto, while if I'm using the largest telescope on Earth, it's going to be a higher resolution dot. But at a certain point, even the biggest telescope on Earth isn't a lot more useful at resolving fine features on objects in space than a telescope that is like a little larger than a consumer. Like you pretty much max out at about a 20-inch telescope is about the most useful size. Like beyond 20 inches, telescopes don't get any better. What makes them better is adaptive optics. And so the larger telescopes here on Earth, they all have an adaptive optic system. What this does, this is shooting a laser beam into space, an artificial star. They then look at the artificial star. They know what shape this artificial star is going to be, and they actively deform the lens of their telescope to mirror the fluctuations that they're seeing in the atmosphere to cancel them out. And it's as if their giant telescope has been sent into space. It's not quite as good as being in space, but it's pretty close. And that's why, like the European Extremely Large Telescope, which is going to be 39 meters across, will be as if you had a very large telescope out in space, because it's able to compensate for the Earth's atmosphere. So for the vast majority of the telescopes out there, the amount and quality of the photons, like the data that they're gathering from space, wouldn't be helping. It's only the best telescopes on Earth, the ones that have these adaptive optics, the big ones. So that's vastly less. But still, you could point all the telescopes on Earth at Pluto at the same time, and you would get the sum quantity of all of their surfaces added together. But one of the things like a lot of people really wonder is like why, when we had, say, the Event Horizon Telescope, we had these telescopes that were far apart. They acted like a telescope. It was the size of the Earth. Couldn't we have all these telescopes on Earth pointing at the same object, and they could be adding their light together, but also you'd be adding the distance of the telescopes to make a virtual visible light telescope that is the size of planet Earth? And the answer is no, unfortunately. Theoretically, You could, but the problem is this idea of interferometry, where we add the light from telescopes that are separated far apart. You need to line up their wavelengths perfectly, down to the few nanometers. And it's just not possible. Like, it can be done with wider wavelengths, like radio waves. Radio waves, the wavelengths can be millimeters or even centimeters apart. And so you can, as long as you have a very accurate clock, you can time when you took images from one telescope, time images when you took from another telescope, and then on computer, line everything up and create the equivalent of a telescope that is as big as planet Earth. But you can't do that in visible light. And so you would need to go to space. You need a space-based interferometer to do this. But the long answer is, like, we talk about this idea of space interferometers, that you would fly these telescopes in space and they would be able to use their separation to be able to get higher resolution images. The other idea that I really like, and I'm surprised that nobody is really investigating this, is that you just add your telescope areas together. That if you have two telescopes with 100 square meters, then you have the equivalent of a telescope that is 200 square meters. And the more telescopes you fly in formation with that telescope and you point them at the same object, they just get more and more powerful over time. And so you can imagine some future where you've got a fleet of telescopes and they just keep adding more and more and more, and they can all look at the same object, they can look at different objects, and you just get this more robust, more interesting telescope. There's like one paper that I saw that came out like 10 years ago, and I even reported on it here on the YouTube channel, and nobody's really dug into it that much. So why don't we do it? Because it's just not practical. Because of the atmosphere, for the coordination. Is it a better use of our time to all look at one target? Is it a better use of our time to look at a bunch of different targets and do astronomy simultaneously in lots of different fields? So I know I'm kind of rambling. I apologize. I have opinions on this one. But yeah, that's why. If you like my answers to your questions, as well as the other things that we do at Universe Today, consider joining our Patreon club. This allows us to keep minimum ads for everybody. Like, as you can see, there are no ads during the middle of this video. As a patron, you also get an ad-free experience on universetoday.com for life, even if you unsubscribe. You get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Tim Whalen, Christopher C2, Ian Cooper, Arne Lubekman, Arda Carduman, Michael Catt, Maria Hirschenbach, Philip Govella, Kevin Townsend, Tim Michalski. Join the club at patreon.com/universetoday. Ben Kalo, you talk of self-replicating probes as if they're inevitable. Rockets, chips, and comm systems require huge manufacturing facilities. Maybe they're just too complex to be possible. Ever. Prove me wrong. I can't prove you wrong. Like, time will prove you wrong. But, like, yes, they're complicated. Ludicrously complicated. But is a chip fab here on Earth designed to make 5 nanometer processor chips the simplest way to build some of these things in space? Can you build one with a 20 nanometer chipset or bigger than that? So I like, this is just a hunch, obviously. And, I'm not the only person to have this hunch that if we, with our meat pinchers, are able to build complex technologies, can we ever build robots that are as dexterous and capable as our fleshy bodies are? And when you look at how quickly technology is advancing, when you see people doing parkour with their robots and you just project that out into the future, like, can you not imagine a time when you've got a robot that's out in space that is mining material and producing complicated things out of raw material? Because robots have a lot of advantages that people don't. Like, they don't get tired, they don't get sick, they are not susceptible to radiation, they don't really care about zero gravity. Like, there's all kinds of upsides for being a robot in space. And the downside for these kinds of challenges is that the things that we want to build are very big and complicated and expensive and require a lot of inputs and parts and machining and bringing in raw materials and all of the stuff that's involved in that. But That all feels like an engineering challenge to me. And you're exactly right. I mean, there's no way that I can prove it. All we can do is watch the continuous march of 3D printing, of space manufacturing. I mean, they're at the point now where they're 3D printing more and more complicated stuff on the International Space Station. A lot of people are proposing different kinds of structures that will be 3D printed in space. I've talked to people who are prototyping building solar cells on the moon out of regolith. So I think there's going to be this balance between them not necessarily being what we would build on Earth. They'll be whatever is the simplest possible way to get that kind of functionality to bootstrap your way up in space. But I feel like to say it's impossible is a reach, because I feel like we'll figure it out. And we may not figure it out today, but maybe we'll figure it out in 100 years or 1,000 years or 10,000 years or 100,000 or a million years. Like, we'll never figure it out. Connor Arroyo. What about the LUVOIR Space Telescope, Fraser? Any updates there? So the LUVOIR telescope, the Large Ultraviolet Infrared Observatory, was planned to be the follow-on, the successor telescope to the Hubble Space Telescope. So it would see the same wavelengths as Hubble, infrared, visible, ultraviolet, but it would be vastly bigger, like a 9-meter telescope, or maybe a 15-meter telescope, or maybe even a 20-meter telescope, like maybe something really big launching on, say, Starship. But we had the most recent decadal survey, and this is where scientists from the US come together and put their list of requirements together. What scientific questions they need funding for to be able to answer. And in that, they decided that the LUVOIR telescope probably doesn't make sense as the next telescope to come after the James Webb Space Telescope. There were like 3 ideas for infrared-ish telescopes. There was going to be HabEx, which would be the Habitable Worlds Explorer. And this would be something kind of James Webb class, but it would be equipped with a sunshade. There was LUVOIR that we mentioned, was like really big. And then there was this one called Origins, which would be sort of like a supersized James Webb Space Telescope that would be able to see the first stars forming, ideally. In the end, they decided to compromise and say, we'll make something that is roughly the size of James Webb, but it will have the star shade. So probably whatever it is, LUVOIR, HabEx, LUVEx, I think is what I've heard, is probably the telescope that they're targeting. It'll be a 6.5 meter visible infrared ultraviolet telescope. So it'll be a little simpler than James Webb, but it will have other places where it gets a lot more complex. Now, I had a pretty long conversation with Lee Feinberg, who is the optics manager for the Hubble Space Telescope and the James Webb Space Telescope, and is working on this next telescope. So if you haven't already seen that interview, we talk about that for a few minutes on what comes next. So there will be a telescope, like probably in the 2030s, that will follow on. And ideally, what's going to make this really interesting is the kinds of science instruments that are on board and its ability to block the light from the star to be able to see the planets next to it. And that's going to be the next generation after James Webb. Brady Photography. Fraser, what do you think are the chances of saving Hubble, and do you think it's worthwhile? Right now, if nobody does anything, the Hubble Space Telescope is probably going to be deorbited in the next decade or so. Now, it's still working fine. It still has lots of reaction wheels, but its orbit is decreasing and it's getting old. And at a certain point, NASA and ESA will make the call, and they will send a spacecraft to dock with the Hubble Space Telescope, and they will deorbit it. Now, that said, a private firm, Polaris, they're the same people behind some of the private space flights. They've proposed sending up a servicing mission that will boost the orbit of the Hubble Space Telescope and give it another decade or 2 at least. And NASA is seriously considering this as a solution, especially since they won't have to pay for it. This private firm is offering to do this. Maybe it'll be like a contract, or maybe they'll just do it as a gift. We don't really know what all the details are going to be. So I think at this point, based on the fact that people are proposing this, I think there's a really good chance that Hubble, like as long as Hubble continues to work, it's still way oversubscribed. Astronomers line up still to be able to use the Hubble Space Telescope. And if there's any way to save it, keep it going for years, decades longer, people are going to try. But also, like, telescopes die. Like space missions just die. And every part in that telescope is getting older and older and older. At a certain point, there's going to be some cascade of failures and it'll stop functioning. It's incredible. You think about like 30 years that telescope has been operational. Like, can we get another 30 years out of it? It would be a mind-blowing achievement if we could. Mr. Monocle, if the universe is expanding away from itself, everything is moving away from everything, how can blue shift exist? Or am I missing something? You're missing something. Blue shift is the indication that something is moving towards us, while redshift is the indication that something is moving away. And when astronomers look at all of the galaxies in the universe, they see that they are redshifted to some degree. Some are redshifted more than others, but roughly the farther away a galaxy is, the faster it's moving away from us. But there are a couple of exceptions, and just a couple. Nearby to us, there's Andromeda, which is on a collision course with the Milky Way. There's Messier 33, which is the big galaxy in Triangulum. There's a few dwarf galaxies that are around us. They're in some shape or form moving towards the Milky Way. And that's because they're on a collision course. We're going to merge in the far, far future. The Milky Way, Andromeda, Triangulum, some of these other dwarf galaxies are all going to merge into one giant elliptical galaxy. And the rest of the galaxies that we can see are all going to fall over the cosmic horizon. They're all going to just be moving away from us faster and faster and faster. And so you do have this expansion of the universe, but in local areas, you can have all these galaxies coming together from all of their mutual gravity, and that is stronger than the momentum of the Big Bang that's carrying everything away from each other, as well as the accelerating effect of dark energy. But it's just a handful. Like, you could probably count the number of galaxies that are blue shifted towards us on both hands, and then that's it. Maybe you need your feet too when you think about all the doors. Anyway, yeah, and so it's just that on the smallest level, gravity is stronger than the momentum that's carrying those galaxies away. But like, there are 2 trillion galaxies moving away from us, redshifted, and a few dozen galaxies that are blue shifted at the most. JR, why have we not made any efforts to send up updated modules to the ISS and break off older modules and adding newer modules every few years or so? It's kind of surprising that once the International Space Station was launched, the plan wasn't just to make this a permanent presence in space and just keep upgrading, adding modules like the ship of Theseus, right? And eventually, 100 years down the road, the International Space Station would be this giant city in space that had just grown organically over time. But the plan is to take the entire station and deorbit it into the Pacific Ocean, and then there will be no International Space Station. There'll be the Chinese space station, and maybe there'll be other missions that will go up, private space stations, but the big International Space Station will be gone. There'll be the Deep Space Gateway, which NASA's going to be constructing, but that'll be it. So why not? And it just comes down to budget, to cost, to expense. Like, the International Space Station is easily the most expensive machine that humanity has ever built. It is hundreds of billions of dollars, well over $100 billion in development costs. It required a collaboration by many, many nations around Earth. It's permanently inhabited by people from Russia, people from the United States, as well as other nations. It's really expensive and it is running down. And so nobody has budgeted an ongoing expense to just start snapping off modules, replacing them with better versions, bringing them back down to Earth. I think that when Starship flies, though, I think ideas that were considered impossible will now be possible. A Starship for a few $100,000, maybe a couple of $1 million, could fly up to the International Space Station, Pac-Man chomp one of the modules inside of it, fly it back down to Earth. They could fix it, repair it, go through it, clean it, get all that fungus out of there, and then refurbish it and then fly it back to space, or replicate it and put a new one on. And so it really just comes down to expense, the expense of building these modules, and then the expense of maintaining them and being able to build out new ones. And like, I don't have an answer for you. Like, I think that maintaining a permanent presence in space, in low Earth orbit, is important. And I think there's still almost endless amounts of science work that needs to be done in microgravity in low Earth orbit. And the International Space Station was the perfect platform to be able to do this. And that era will come to an end within a decade from now when they deorbit the whole thing. But as with Hubble, right? Like who knows what really is going to happen? Like, will the various space agents just continue to figure out ways to extend its lifespan forever and building it up over time, as you mentioned? And I think the thing that will be the pivotal change to this is going to be Starship. If Starship works and it is inexpensive and it is reusable, then I think a lot of missions that were considered to be end of life, now something could have a second lease on life. I can even imagine them bringing the Hubble Space Telescope back down to Earth for complete refurbishment. That would be awesome. So stay tuned on that. We just need Starship to work. All right. Those were all the questions that we were able to get through today. Thank you everyone who asked questions in the YouTube comments. Thanks everybody who joined for the live show. It's a lot of fun. We do this every Monday at 5 p.m. Pacific time. And don't forget to vote. Vote in the comments down below for the question that you liked the best. If you want to stay on top of all the important space news, join my weekly email newsletter. I send out every Friday to more than 60,000 people. I write every word. There are no ads and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Gerge, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbioff, Josh Schultz, and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us.